340 kilometers of enemy airspace. No escort. No jamming aircraft flying alongside. No return flight programmed into the guidance system. The drone didn't need to come back. What it needed to do was survive long enough to reach a facility Russia considered untouchable, a naval aviation maintenance base so far inside the Russian interior that Moscow's defense planners had stopped thinking seriously about protecting it from the air. The distance itself was the shield. That was the doctrine. That was the assumption. Assumptions are expensive in this war. I'm your host at UkraineRadar, where we analyze the battles that change wars. Today's reconstruction follows one of the most precisely engineered long-range UAV strikes of the entire conflict. A mission that required months of satellite intelligence collection, multiple failed approach rehearsals, 3 separate terrain masking route adjustments, and an operator team that had to watch their creation disappear over the horizon and then simply wait. What burned on that helicopter apron redraws Russian naval aviation capability for the foreseeable future of this offensive. And it started not with a launch order, but with a question someone in Ukrainian military intelligence asked while studying satellite imagery of a facility no one expected Ukraine to reach. Why are 3 of Russia's most capable, carrier-capable helicopters sitting wing-to-wing on an open maintenance deck? That question became a mission. The mission became a strike. And the strike became the story we're breaking down today on UkraineRadar. To understand what made this target significant, you need to understand what Russian naval aviation has been trying to accomplish since the full-scale phase began. Russia's Black Sea Fleet lost surface superiority to Ukrainian maritime drones and precision missiles long before this strike. Neptune anti-ship missiles, surface drone swarms, Storm Shadow cruise missiles delivered from Ukrainian aircraft. The attrition campaign against Russian naval surface capability had been methodical and punishing. What Russia retained was its rotary wing naval aviation component. Helicopters assigned to anti-submarine warfare, maritime patrol, amphibious assault support, and ship-based operations. These platforms are not replaceable quickly. Russia's defense industrial base, strained by years of sanctions and wartime production demands, cannot manufacture new naval aviation helicopters at the rate the war is consuming equipment. Every Ka-27, every Ka-52K, every Mi-14 variant lost to Ukrainian action represents a capability gap that takes years to close, not months. The facility sits deep in the Russian interior, at a distance from Ukrainian-controlled territory that had historically placed it outside the operational range of most Ukrainian strike systems. Moscow's Naval Aviation Command picked it precisely because of this geographic insulation. Workup cycles for helicopter crews between deployments happened here. Maintenance schedules, avionics upgrades, weapons system calibration, all of it conducted at this installation under the assumption that they were beyond reach. Ukrainian military intelligence didn't accept that premise. The collection effort began with satellite imagery analysis, cross-referenced against signals intelligence indicating unusual activity at the facility. Pattern of life analysis over multiple weeks established the routine. When helicopters arrived for maintenance cycles, how long they typically stayed, which aprons were used for specific maintenance categories, and, critically, when multiple airframes would be present simultaneously in close proximity on the open deck. 3 helicopters on a single open apron is an intelligence collector's ideal targeting scenario. The goal was to be overhead when that configuration repeated. The route planning phase is where the mission nearly collapsed before it began. The straightest path between the launch zone and the target facility passed through radar coverage from at least 4 known Russian air defense installations. Crossing those coverage zones at the altitudes necessary for efficient UAV flight would have meant detection, interception, and mission failure. The drone team needed a different approach. Terrain masking is the technique of flying below the effective horizon of ground-based radar by using the Earth's own surface features, ridgelines, valleys, river courses, forested elevation changes, as a shield against radar line of sight. At low altitude, a radar beam that travels in a straight line simply cannot see targets that are physically below the geometric horizon created by intervening terrain. The drone becomes invisible, not through electronic countermeasures, but through geography. Ukrainian mission planners spent weeks mapping the terrain profile along every candidate approach corridor into the target area. They were looking for a path that combined 3 elements: sufficient terrain masking to stay below radar horizons at the critical detection ranges, flight distances that fell within the drone's operational endurance at the planned payload weight, and a terminal approach vector that would place the weapon system directly over the maintenance apron at the angle required for maximum structural damage. The first candidate route was rejected because a section crossed open flat terrain with no masking features for a sustained stretch that exposed the drone to a radar installation at under 40 kilometers. At that range, even a low radar cross-section target would likely generate a trackable return. The second route added too much distance. The drone's fuel margin at that total flight path length became unacceptably thin. A single unexpected headwind component at any point in the 4-plus-hour flight could bleed the remaining fuel reserve to zero before reaching the target. The third route, the one that ultimately flew, threaded a river valley system for a significant portion of its approach leg, exploiting the elevation differential between the valley floor and the surrounding terrain to stay below effective radar coverage. It added approximately 60 kilometers to the total flight distance compared to the direct path, but it preserved the fuel margin and kept the drone invisible to the specific radar installations that posed the greatest interception risk. Which weapon type do you think was most decisive in enabling this strike? Was it A, the terrain masking navigation system that hid the drone from radar? B, the explosive payload design that maximized structural damage? Or C, the satellite intelligence that identified the optimal targeting window? Drop your answer in the comments. We'll break it down at the end of the video. The route adjustment also required a modification to the drone's navigation system waypoints. UAVs of the type used in this mission don't fly by GPS alone. Russian GPS jamming has become sophisticated enough across Russian territory that a purely satellite navigation-dependent system is vulnerable to spoofing or signal denial. The Ukrainian drone used an inertial navigation system cross-referenced with terrain-matching technology, comparing its sensor-derived picture of the ground beneath it to preloaded terrain elevation maps to continuously verify and correct its position. This was not improvised technology. It was the product of a development program that had iterated through failures, worked through jamming scenarios and testing, and arrived at a solution robust enough to operate across hundreds of kilometers of contested and denied electronic environment. The drone was loaded with a shaped warhead optimized for the target type. An open-air maintenance facility is not a hardened bunker. It doesn't require a penetrating munition designed to punch through reinforced concrete. What it requires is a warhead that maximizes burn and blast effect across the open apron, igniting fuel and hydraulic systems in the aircraft parked on it, creating secondary fires that sustain themselves even after the initial detonation energy has dissipated. The payload weighed within parameters that kept the drone's flight performance within the margins established during route planning. Not a kilogram more than necessary. Stay with me. What happens in the next segment completely changes how you understand what Russia saw on radar in those final minutes before impact. The launch happened in darkness, from a location UkraineRadar will not specify for operational security reasons that remain valid. The drone rose to initial flight altitude. Its navigation system executed the first waypoint turn, and it disappeared into the night sky heading east. For the next several hours, the operator team had nothing to do but wait. This is one of the psychologically unusual aspects of one-way UAV operations that doesn't get discussed enough. The launch crew sends the system off and then enters a period of complete operational disconnection. They cannot redirect it mid-flight through most of its course. They cannot abort it if something changes. The drone flies its pre-programmed route, makes its navigation corrections autonomously, and the humans who built the mission, planned the route, and loaded the warhead are sitting at a console watching a telemetry feed and waiting for confirmation that takes hours to arrive. The psychological weight of that waiting period is its own kind of operational stress. 4 hours and 17 minutes after launch, the drone entered what mission planners had designated the terminal approach phase. This is the final segment of the flight, where the terrain masking route gives way to the last stage pop-up maneuver that brings the weapon system from its low-altitude masked approach to the attack angle required for effective warhead delivery. Russian air defense radar operators at the facility's associated sensor network had been scanning their screens through a routine watch rotation. The facility was a rear area installation. Air defense posture at locations far from the active front reflects a different threat assessment than installations near the contact line. Rotations are longer, attention drifts, the procedural edge that comes from genuine expectation of engagement degrades over time. The first radar return from the approaching drone appeared on a sensor screen as what operators initially assessed as a ghost track. At the drone's approach altitude and with its terrain masking flight profile, the radar energy reflecting back was marginal, barely above the noise floor of the detection system. The return appeared, disappeared, reappeared, slightly displaced. Classic characteristics of ground clutter interference or atmospheric anomaly. The operator logged the return. Standard procedure. He did not escalate it to an interception alert. 22 seconds later, a second operator at a different console picked up the same return on a slightly different sensor. Same assessment. Probable clutter. The procedural response to probable clutter at a rear area facility is notation, not scramble. The drone crossed the final terrain feature providing radar shadow, initiated its terminal climb, and acquired the target through its optical seeker. 3 helicopters, wing to wing on the maintenance apron, exactly as the satellite imagery had predicted. the terminal dive began. What would you have done differently if you were the Ukrainian mission planner facing a 400-kilometer no-return flight over defended territory? Think about that question, because the decision architecture behind this mission reveals something important about how Ukraine fights this war. The warhead detonated on the reinforced concrete apron between the first and second aircraft, precisely within the kill radius designed to affect all three airframes simultaneously. The blast wave and primary fragmentation pattern spread across the parking configuration. The incendiary component of the payload ignited immediately. Fuel from ruptured tanks in the nearest helicopter providing the first sustained combustion source. Secondary fires developed within 90 seconds of the initial detonation. Hydraulic fluid in the maintenance-staged airframes provided additional fuel. Fire suppression systems at the facility were not positioned for a scenario where three aircraft ignited simultaneously in the center of an open apron. The coverage geometry wasn't designed for that event sequence. Satellite imagery analysis confirmed by multiple open-source intelligence verification efforts showed the extent of the damage in the hours following the strike. All three airframes were assessed as destroyed or damaged beyond practical repair given Russian maintenance capacity in the current operational environment. The maintenance apron itself sustained structural damage consistent with the warhead type and yield. The facility's ability to conduct rotary wing maintenance operations was assessed as significantly degraded for an extended period. Not eliminated, ground facilities are more repairable than destroyed aircraft. But the combination of lost airframes and disrupted maintenance throughput creates a compounding effect on Russian naval aviation readiness that extends well beyond the physical damage visible in the imagery. Subscribe to UkraineRadar if you want to understand how modern warfare actually works. Because what happened after the smoke cleared reveals something about Russian command response that's just as important as the strike itself. Russian Air Defense Command's initial response to the strike report was, according to intercepted communications analyzed by Ukrainian intelligence, a period of confusion that lasted longer than it should have. The facility's distance from the front and its classification as a low-threat installation meant that the command and control infrastructure for responding to a successful strike on it was less developed than at installations closer to the contact line. Communications intercepts indicated initial reports from the facility described the event as a possible accident, a maintenance-related fire or fuel system failure. The possibility that a long-range Ukrainian UAV had successfully navigated several hundred kilometers of Russian interior airspace and accurately struck a specific maintenance apron was not the first assessment that emerged from the facility's own reporting chain. This delay in accurate assessment is itself operationally significant. Every minute that Russian Air Defense Command spends processing an attack incorrectly is a minute not spent adjusting radar coverage, repositioning assets, or identifying the ingress corridor the strike used. That corridor stays available for future missions until Russian planners identify it and take corrective action. The attack exposed a gap in Russian defensive doctrine that their military had considered theoretical. The assumption embedded in their layered air defense architecture was that strategic depth, the simple geographic distance from Ukrainian-controlled territory to these installations, provided passive protection that didn't require active air defense coverage at the same density as forward areas. That assumption turned out to be a vulnerability. If you believe tactical innovation beats institutional inertia in modern warfare, type UkraineRadar in the comments. Because what Ukraine demonstrated here applies to every asymmetric conflict in the modern era. The corrective measures Russia would need to implement are neither simple nor cheap. Extending meaningful radar coverage to every installation currently operating under the assumption of geographic protection would require substantial investment in sensors, processing infrastructure, and the operator manpower to run them continuously. Russia's defense industrial base and military manpower system are both under strain from the demands of the ongoing offensive. The alternative: relocating critical aviation maintenance functions to better protected facilities, carries its own costs in logistical complexity, operational disruption, and the time required to establish equivalent maintenance capability at new locations. Ukraine demonstrated something with this strike that its forces have been demonstrating across multiple domains of this conflict. The willingness and ability to invest months of planning effort into a single precise operation, targeting a specific capability, and then execute that operation with sufficient technical sophistication to reach targets. Russia considered protected by geography alone. This is not how Soviet-era military doctrine conceived of the threat. Ukraine is not fighting by Soviet playbooks, and Russia, in significant ways, still is. The intelligence collection effort that identified this targeting opportunity and the mission planning work that created a viable approach route both represent capabilities Ukraine has built and refined throughout the extended period of this conflict. They are not improvisational. They reflect institutional learning at a rate that has consistently outpaced Russian adaptation. The drone operators who launched this mission and then waited through hours of telemetry silence before confirmation arrived. They are the modern expression of what UkraineRadar means when we say Ukraine doesn't just use weapons. Ukraine invents new ways to fight. A one-way aircraft threading a terrain-masked route through hundreds of kilometers of defended airspace to strike a specific maintenance apron is not an inherited tactic from any previous doctrine. It was engineered for this conflict, for this target set, against this specific defensive architecture. What NATO would have approached with manned strike aircraft and dedicated electronic warfare support, requiring coordination across multiple platforms, airspace deconfliction, and significant risk to pilot lives. Ukraine accomplished with an autonomous system costing a fraction of the alternative and carrying no crew risk whatsoever. That asymmetry, in cost, in risk, in tactical flexibility, is the central lesson of this strike. The question of what this means for other facilities Russia currently considers geographically protected is not theoretical for Russian air defense planners. It is an immediate operational concern that requires resource allocation decisions against a constrained budget. The answer to our quiz from earlier in the video: the terrain masking navigation system was the critical enabling technology. Option A. Without the ability to stay below radar horizons along the approach corridor, the drone would have been detected by one of the 4 air defense installations along the direct route and engaged before reaching the target. The explosive payload and the satellite intelligence were both essential, but neither could deliver results if the drone was intercepted during approach. The navigation system made everything else possible. It was the technical foundation the entire mission rested on. Was the decision to use the longest terrain-masked route, adding 60 kilometers and reducing fuel margin, the right call given the alternatives? Could Russian air defense have prevented this if their radar coverage had been positioned differently at those specific terrain features? And what would you have done as the mission planner if the third candidate route had also been rejected? Would you have scrubbed the mission or started the route planning process again from the beginning? Comment your tactical assessment below. We read every response. Real tactics, real consequences. UkraineRadar. Subscribe to UkraineRadar. Because we break down the battles that textbooks will study for decades. The maintenance apron is quiet now. The wreckage has been partially cleared, according to subsequent satellite imagery. But the outline of where 3 aircraft sat wing to wing is still visible in the damage pattern on the concrete. A silent record of the moment Russian geographic assumptions met Ukrainian engineering precision. Modern warfare punishes tactical assumptions without mercy. Stay vigilant.